Hello dear students of +1 medical and non-medical respected teachers. So today I am going to discuss a very important theorem which is known as Bernoulli's theorem. So I will discuss its statement, its derivation as well as applications of Bernoulli's theorem. So let us start. So statement of Bernoulli's theorem first. Bernoulli's theorem states that for an ideal fluid means which is non-viscous and incompressible, the sum of pressure energy per unit volume, that is P, kinetic energy per unit volume, that is half rho V square, gravitational potential energy per unit volume, that is rho GH, is always constant, provided the flow is slow and steady, that is streamlined, where P is called pressure, rho is density of the fluid, V velocity of fluid, H height at which fluid is flowing. So to prove it, suppose we have a tube of flow PQ. Tube of flow means bundle of streamlines flowing together. So tube of flow PQ of this shape. Let H1 is the height of the center of the and P of the tube from the ground. H2 be the height of the center of the end Q of the tube from the ground. So that H2 is greater than H1. Let A1 is equal to area of cross section of the tube of flow at end P, A2 area of cross section of the tube of flow at end Q. Rho 1 density of the liquid at end P, rho 2 density of the liquid at end Q. V1 is the velocity of the liquid at end P, V2 is the velocity of the liquid at end Q. P1 is equal to pressure at end P and P2 is the pressure at end Q. Then, since a slow and steady or streamlined flow of the fluid, maybe liquid or gas, is flowing through this tube of flow from end P to end Q, so suppose the liquid is pushed through distance L1 at end P, say per second or any given time, and let liquid comes out of the tube of flow at end Q and covers distance L2 in the same time. Then at end P, amount of work done in pushing the liquid through distance L1 is given by W1 is equal to F1 L1, or F1 is P1 into A1, force pressure into area, or W1 is equal to P1 into V, where V is equal to volume pushed per second per unit time. P1 A1 L1, A1 L1 is equal to V, volume pushed. So this is the amount of work done on the liquid in pushing the liquid. Then at end Q, amount of work done by the liquid. So liquid is coming out through end Q itself. So amount of work done by the liquid at end Q through distance L2 is given by W2 is equal to F2 L2 or P2 A2 L2 or P2 into V. Because A1 L1 is equal to A2 L2 is equal to V, because the liquid is incompressible. So you have taken liquid which is incompressible. So the volume pushed per second must be equal to volume coming out per second from end Q of the tube of flow. So this is work done upon the liquid at end P, this is work done by the liquid at end Q. Then net work done by the liquid is given by W is equal to net work done on the liquid. Net work done on the liquid, W is given by work done upon the liquid minus work done by the liquid, W1 minus W2. or P1 minus P2 into V, or this is it, number 3. So this gives net work done upon the liquid of volume V. Now, suppose this is equation number 3, this work that we have done. Now, since area of cross section in this figure A2 is less than A1, therefore velocity V2 will be greater than V1 because of equation of continuity. A1 V1 is equal to A2 V2, or AB is equal to constant. Product of area of cross section and velocity is always constant. This is known as equation of continuity. That is, volume flowing per second at n_p must be equal to volume coming out per second at n_q. So, therefore, if velocity increases, mass coming out remains same, volume coming out remains same, it means it will gain kinetic energy. So, gain in kinetic energy of the liquid is given by half mv2 square minus half mv1 square, or half m common v2 square minus v1 square. Say this is number 4. Since h2 is greater than h1, there will be gain in gravitational potential energy. So gain in gravitational potential energy is given by mgh2 minus mgh1 by definition, or mg common h2 minus h1. Say this is number 5. So by law of conservation of energy, work is done upon the liquid. Part of it is converted to gain in kinetic energy, part of it is converted to gain in gravitational potential energy. So therefore, equation 3 must be equal to equation 4 plus equation 5. That is, P1 minus P2 into V must be equal to half mv2 square minus v1 square plus mg h2 minus h1, or P1 minus P2 is equal to divided by volume throughout, half mass per volume is rho. So half rho v2 minus v1 square plus half rho g h2 minus h1, because mass per volume is equal to density, or P1 plus half rho v1 square plus rho gh1, taking to left hand side, so it will be P2 plus half rho v2 square plus rho gh2. Now what is P1? Pressure energy per unit volume at np, kinetic energy per unit volume at np, and gravitational potential energy at np per unit volume. Similarly, P2 pressure energy per unit volume at q, half rho v2 square, kinetic energy per unit volume at nq, rho gh2, gravitational potential energy at nq per unit volume. So it means total energy at P and P is equal to total energy at N Q. In other words, so we can write P plus half rho V square plus rho GH is always constant, which is nothing but Bernoulli's theorem, which states that for an ideal fluid which is non-viscous and incompressible, and for the flow is streamlined, that is slow and steady, sum of pressure energy per unit volume, kinetic energy per unit volume, and gravitational potential energy per unit volume is always constant. This is known as Bernoulli's theorem. Another form, if we divide this equation by rho through P upon rho half V square, and GH is equal to constant. It is also constant. Density of liquid is constant. So it means sum of pressure energy per unit mass, kinetic energy per unit mass, gravitational potential energy per unit mass is always constant for an ideal fluid, and for the flow is slow and steady, that is streamlined. So it means this is another statement in terms of energy per unit mass. If we divide by G throughout, it will be P upon rho G plus half rho V square upon G plus H is equal to constant. So P upon rho G half V square upon G and H. And this is known as pressure head, this is known as velocity head, this is known as potential head. It means another statement, for an ideal fluid, the sum of pressure head, velocity head and potential head is always constant, provided the flow is slow and steady, that is streamlined. So these are three different statements of Bernoulli's theorem. Now, special case for a laminar flow. So laminar flow is a special case of streamlined flow, in which the tube of flow is horizontal, that is H1 is equal to H2 is equal to H say. It means if height remains same of the tube of flow, there is no gain in potential energy. So we have all two terms, P plus half rho V square is equal to constant. So where P is called static pressure and half rho V square is called dynamic pressure. So it means from this equation, for an ideal fluid and for laminar flow is a special case of streamlined flow, the sum of static pressure and dynamic pressure is always constant. And from this equation, in nutshell, what is the basic principle of Bernoulli's theorem? When pressure increases, velocity decreases, so that this sum remains constant. When pressure increases, velocity decreases, and vice versa. That is, when velocity increases, pressure decreases. So this is the main point of Bernoulli's theorem, which states that when velocity increases, pressure decreases, and vice versa. Or when pressure increases, velocity decreases. So this is statement and derivation of Bernoulli's theorem. And there are so many applications of Bernoulli's theorem in daily life. We have seen during dust storm, the roofs of the huts are blown off. Why the roofs of huts blown off? Due to Bernoulli's theorem. Because there is atmospheric pressure inside or outside the hut. When velocity on the roof of the hut increases, pressure decreases. So due to excess pressure inside, the roof of the hut is blown away. So that's why the roofs of the huts are blown off during dust storm because of difference of pressure inside or outside. Above the roof, pressure decreases and velocity increases due to storm. Principle of atomizer. Any spray pump, sand spray, we press the top spray, we get spray sent in the form of spray. What happens? Due to Bernoulli's principle. When you press, velocity increases, pressure decreases, scent or liquid rises through a pipe inside the bottle, then mixed with the air and comes out of the nozzle in the form of spray. So any spray pump like atomizer is based on principle of Bernoulli's theorem. Similarly, principle of Bunsen burner or gas burner. Well, for gas burner there is a fine nozzle. So when velocity increases, pressure decreases. So therefore, oxygen enters, air enters, so it gets ignited. Why flag flutters? Chanda ka chul hai. So flag flutters because as we go up, velocity increases and pressure decreases. So flag's cloth has certain length and width. So it experiences different pressure at different points because of height. That's why, so it flutters like this. So why flag flutters? You can say due to Bernoulli's theorem. All trees on the roads, we have seen trees on the roads or highways are bent towards the center of the road. Because when traffic goes with high velocity, pressure decreases. So they grow, when they grow, so they bend toward the region of lower pressure, that is toward the center of the road. Motion of ping pong ball. Take a cap of ink pen, there is a fine hole, and blow air. Put ping pong ball just above the hole and blow air through the mouth. You will see ping pong balls attain some height, and if you continue blowing air, it stays there at certain height and dances. This is the motion of dance of ping pong ball is also due to Bernoulli's principle. So there are so many applications. In next video, I will discuss Torricelli theorem, which is also application of Bernoulli's principle. So Bernoulli's principle is very, very important, and I think I have explained in a very good manner. So repeat it. All the best. Be happy. Good luck. Stay tuned. Our next video. All the best. Sarvat Dapa.